All right, everyone. So I talked to the university about what to do about the birds, and they had no solution, so I brought in my dog. That's my real dog. His name is Barky, and he seems to be keeping the birds away, so we'll keep him around for a while until, I don't know, maybe we'll get an owl or a monkey or something to get rid of him. In the meantime, welcome back. Today is hour 3 of our 45-hour lecture series. Now recall that unlike the schedule in the UIC catalog, I'm going to do lecture first and then the extra hour after. The extra hour, I'm not going to lecture during that. That's supposed to be question and answer time, which is totally not going to work under the present circumstances. And, excuse me, and to be honest, it never really did. I ask people for questions and no one ever responds. I'm not going to waste the hour, so I usually have prepared lectures. So, and I've been doing that for years, so I don't really see any reason to stop. What I'm going to do is work problems. So you don't have to ask me to work a problem for me to work a problem. I'm just going to work problems. Now, we are obviously early on in this course, so what I'm going to do is I'm going to work problems that I know that are going to be on the test and cover some background material. And I'll be doing that easily for the first month. Like multivariable calc. I know you haven't had that, so I'm going to be covering a lot of that stuff. And I'll need more than just 1 extra hour. And it will be relevant to the test, and I will explain it by working example problems. So that's what I'm going to do with these extra hours. Okay, so with that said, I often will talk about the material that I cover in this hour in the extra hour. And that's why I'm going to do it second. If you don't feel like watching it, you can easily still pass this class with an A. However, it would be harder. So in terms of maybe you already know the material because you're kind of more at the math end of things, fantastic, you get an A, who cares? However, I would suggest that my ability to get you up to speed by watching me tell you what you need to know is better than trying to figure it out on your own. I think that's fair. I wouldn't presume that necessarily, but probably. All right. Anyway, what did we talk about last time, right? We always review. What we were doing last time is we're on Maxwell-Boltzmann. This is the first week. We're going to do one more week, and then we're going to start on quantum. Maxwell-Boltzmann starts with the Boltzmann equation, with how nature partitions energy. And what is that good for? It's good for, you're going to see what it's good for more today. I know this has been really abstract, especially this normalizer part on the bottom, right? Remember I call it the normalizer because we think of probability, think back to lecture 1 on Monday. What's the probability of getting heads on 2 flips of a coin? It's 1 out of 4 because that was 1 result out of 4 possibilities. So I always call it the denominator, I call that the normalizer. Okay, again, this is the Boltzmann equation, it's how nature partitions energy. I'm looking at this and, okay, it doesn't look that bad, but I'm just not sure how to use it. I'm not sure what it means. It will be very clear what you can use it for today. It has not been clear, nor, if you feel like you're not sure where this is going, that is how you should feel, because I haven't really covered it yet, because it takes a while to get there. Okay, now think about the steps that we took. For one, I have to define what the energy is. This is how nature partitions energy. But there's all kinds of energy. Vibrational energy, rotational energy, translational energy, and we're doing translation. And one of the other ways I simplify this is, let's talk about argon gas, which can't vibrate or rotate, right? So that way we can eliminate those. So we're doing translation. And again, we're doing it because it's not that hard, and there's a lot of cool things that you can see from it. Like today, I'm gonna go ahead and give you the answer. Can a gas molecule move faster than the speed of sound? Yes, it can. Isn't that weird? I'm going to prove it today. I mean, that is so weird, but it's true. Sound is a pressure wave, and I guess velocity is not that. The velocity of a gas molecule is not that, and I just don't get that. But anyway, you're going to see that today. Okay, so I plug in 1/2 mv squared into the energy. So now I have a probability distribution of velocity. It's still energy, but it's velocity, because there's no E in it, but it's still energy. It's both at once, and that also messes with my head. Okay, Now, the next part is to deal with the normalizer, right? This sum looks very abstract, but I mentioned to you the way that you can think of this sum. We divvied it up into x, y, and z. That's a detail, don't need to worry about it. But it's valid to think of this as a sum because I mentioned a little quantum mechanics. When a gas atom is trapped in a box, it doesn't move with any velocity. It moves in discrete steps of velocity. And you would need that to solve a sum, right? The sums are discrete, the addition of discrete things, a plus b plus c, where the discrete things are the a, b, and c. Those require specific values of velocity. So I explained a little bit about how that works, and it'll be more clear when you actually prove that using quantum mechanics. Okay, the next step was to turn the sum into an integral. We used an identity, and then we got the normalizer, right? And that's what that turned into. The 3, so again, this is from the normalization. The 3 halves, the 3 comes from the fact that we live in 3 dimensions. The 3 halves, the halves part, the 1/2, that just was the solution to from the identity, the calc identity that we used. That is how you're going to do your homework and your exam questions. This part is still just from the Boltzmann distribution. And then where we ended off last time was talking about this dvx, dvy, dvz. Okay, pain in the rear. I have 2 approaches. One is to turn net velocity squared into vx squared plus vy squared and vz squared. And cool, all right? You're going to do that on some homeworks. And those are really easy problems. And we're also going to do a problem like that, I think on Friday next week. Okay, but what you don't get from that is the ability to calculate net velocity. And that ends up being useful for all the reasons you're about to see. That is how I'm going to be able to do something like, you tell me, I have a gas. Oh, what gas is it? Oh, it's argon. Okay, tell me about argon. Tell me its mass. Yada, yada, yada. You tell me this, and then I can tell you what the pressure is of argon at room temperature. I can do that with net velocity. You're going to see that, I think, next Wednesday. Cool, right? But that means that I'm going to keep this, and I have to change this. Now, I talked about how to do that. I take dvx, dvy, dvz, divide by the partial of net, times the partial of net. Notice that it hasn't actually changed. The trick is that this is actually going to be an expression. This looks like a derivative, right? It's like dy dx. That's what it looks like. And like a derivative, it can be evaluated, and it's going to just turn into a function. Now, there's 2 ways to do it. I'm going to show you a graphical way to understand it now. And that is appropriate for this class. In the next hour, I'm going to show how to do the bloody 3-dimensional multivariable calc to solve it for real. And I'm not going to put that on a test, but it is the way to do it. So I really am obliged to show you that. So that will be in the next hour. But now, as I promised, for this hour, I'm going to show you a graphical way to understand what a Jacobian is. And it turns out that this is a simple function, and then we have our Maxwell-Boltzmann distribution. Okay, now to do this is going to be a little funky. Now, you've already seen, mostly on Monday's lecture, that I can add some visual elements into the class, but I swear to God, this is so much harder than it looks. I'm learning to do this for the first time because of COVID. It's really hard for me to interact with something I can't see. So now I really appreciate actors in green screens, right? I always thought that was cheap, but it's actually really freaking hard to interact with something that's not there. So I want to show you some really nice visual graphs. So I had to do it digitally, but it's not actually here. So this is a little rough for me. So sorry if this doesn't come across as well as I would like to try. All right. Now, to get started on this, we're going to look at what we're going to integrate like f of x. And I did a little bit of this last lecture. I'm going to draw what I'm going to do so that I can interact with it, but then I'm going to do the digital. In fact, hopefully I'm already doing it right now, showing you what it is I'm kind of planning here. So here, this is for my benefit. So I'm going to graph a function, and it looks like this. This is kind of like what I've done on the digital. And I want to remind you of like how Simpson's rule, integration by rectangle. that's what I'm doing here. And of course, that's also what you're seeing. I think that's what you're seeing in the digital part. I made all that. I made all that some time ago. I haven't looked at it in a while, so I can't say that I remember offhand exactly what it looks like. Okay, now regardless. Okay, so what you're seeing is a function. That's the slanting curve, and we're going to integrate it. And you know that you can simply create a bunch of rectangles, the area from which is very easy to calculate, and sum that up. Now, the y is determined by the function. The height is the function at point x. The width is the partial of x. Okay, there you go. Like child's play. Now remember that the fundamental theorem of calculus, or actually I don't know what the fundamental theorem of calculus is, but I think what it is that like calc works like when the partial is like infinitely thin, but I can't draw that, can I? So I've drawn it with some width. Now, as for which part, this is like 0, 1, 2. So am I using f of x of 1 or 2? Looks like in this example, I've used f of 1 to figure out the height. So this rectangle's area is determined by whatever this width is. So if this is like 0, 1, 2, then dx is 1. And it looks like the height is f of x, where x is 1. Look, the details, it doesn't matter. I just want to make sure that you understand what I've drawn here, or what is there. God, this really is hard, by the way. Anyway, all right. Okay, so what? I just want to remind you what a partial is. Here's how to start to understand Jacobians. Now, what I'm going to tell you is not relevant to our problem, but I want to make sure we're on the same page, that we understand partials. And what we're doing is we're transforming our function, our integral is going to go from an integration of x to y. That's what I'm doing here. You'll understand why that's relevant to our problem here in a minute, but let me describe how that works. Okay, so I have a function, f of x, and let's say that I'm going to, instead of integrating f of x, let's say I'm going from 0 to infinity, that doesn't matter. Let's say that I have y, which is equal to x squared. Now, in our little example here, imagine like y is energy, and x would be velocity, right? 1/2 mv squared is energy. Energy is basically velocity squared. Okay, so that's kind of the analogy. All right, now the point of this is, what I want to do is change this integral from x to y. Okay, now the trick is, wherever you see an x, you would write what? Wherever you see an x in this function, you would write the square root of y, right? Because x is equal to the square root of y, right? So, hey, that's actually half of it. That's half the problem. It's pretty easy. Okay, now here's where it gets a little rough. You might want to just do this. Just write partial of y. No, here's why. These rectangles that you're seeing, this partial in x is not as wide as the partial of y, right? Because y is the square of x. Again, you can't just say that the partial of x is the partial of y. They can't be the same width because they're not the same function. Obviously, y being the square root of, x is the square root of y. It looks like y is probably thinner, I guess. All right, now here's what you do. One thing is, remember that you can't really ever change anything. So I've got f of x and I've got f of x. Now x is a function of y. So wherever you see an x, write the square root of y. Very simple. Okay, but I still have to have dx. So to get dy, I divide and multiply by dy. Okay, and there's our Jacobian, dx dy. Now how does that work? Well, hold on, I've got it right here, right? Let's see. Therefore, y is the square root of x, and what have I done? Wrong. Therefore, square root of y is equal to x. So dx dy is the change in the square root of y. I always use to the 1/2 when I'm doing derivatives. It's a little bit easier. Right? So dx dy, where x is the square root of y, there you go. Okay, so to turn this integral into a function, into the same, but integrating y instead of x, all you do is you multiply it by y to the 1/2. Okay, and that's what a Jacobian is. Okay, now I'm going to go over this again and again in the next hour, but the point is, here's the point, is that the change in y and the change in x require a scaling factor because they're not the same width, right? You see how the width matters to the area. So you can't just say dx is dy. They're not the same width. The Jacobian is the scaling factor such that you get the right areas. That's the big picture. That's the point. Okay, now with that said, that is just to make sure that you really, really get partials. But now we're going to get to another whole level, which is a little painful, and that is to see, now I've changed the image, and now what you're seeing is a two-dimensional integral of dx dy. Here, let me write that. No, I think I have that in the image, right? Actually, I don't recall. I think I have it in the image. So I told you this is hard. So let's say we're doing a two-dimensional integral. Okay, now this is what is relevant to our Maxwell-Boltzmann deal. Here in the image, you see that partial x, partial y is like this, it's like this. It's an area. Delta x, delta y. That's an area. If each one is 1, then the area is 1 squared, which is 1. Right? Okay, if each side is 2, then the answer is 4. The area is 4. So the partials are just an area. Now, why is that important? Now, let's think about, in the last image I showed you, as you integrate, you take these steps, partial x. You keep walking what you were walking from the left to the right. Now we're going to do that, but instead of taking steps, what we're doing is we're creating area. Okay, now I'm going to go off on my own. All right, now in that graph that you see, let's look down on the x and y plane. So we're looking down. I know in that image I'm showing it's a little bit cockeyed, so you have a little bit of a visual. But now let's look straight down on it. Okay, so the partial x, partial y is this area. Okay, now just like in the previous one-dimensional example, let's start taking steps forward and see how this area changes. Well, it's not too hard, right? Now remember, you're going to go up, down, left, right, side to side. So the area is just an area. It's just growing. Now remember that we're going to do this an infinite number of times, and that these steps are actually kind of small. This is gigantically exaggerated, right? These steps in x and y and up and down and left and right, they're infinitely small. So that means after you've done a few, what you're going to have is something that kind of looks like a circle, right? So I know I'm not doing such a great job, but anyway, here's the idea. After you've done a whole bunch of these, the area is growing like a circle. Okay, cool, whatever. Our mission is to change these partial x, partial y into the net. Now, for vectors x and y, r is the square root. R is the net, right? R is the net length. That's x squared plus y squared. Right? This is very 8th grade trig, right? Or 9th grade, 10th grade. You had trig in 10th grade. Okay, you learned this in 10th grade trig. Now what I want to do, the mission here is to change dx, dy into change in the net. How do you do that? Now you can start to see a little bit how we're solving the problem that we're trying to solve. How do you change partial vx, vy, vz to partial net velocity, right? This is just a 2D analog of that. This is going to teach us how to do this. Going to 3D is just one layer of complication anyway. Okay, so as we work our way through the integral, think about the last example, as we work our way through the integral, as you take more and more steps in x and y space, and again, you know, it's the circle's not perfect because you're taking discrete steps in x and y. I'm not doing such a great job with that, but anyway. As you are going forward in the integral and adding up those areas, how does the area scale with this growth, right? And this is dr. Okay. Now again, the R tells you how far you've gone out in x and y. What we're trying to do is figure out how this integral changes, not as the partial on x and partial on y, but as the net, whereas the net is a radius, is the square root of the x squared plus y squared, right? Just like, again, high school. Okay, so how does that work? How do I represent the area, not as a function of x and y, but a change in x and y, but a change in r? How do I represent that area? Now, the trick here is to notice that as this thing grows, it's the area of this disk. You see? When the question is, what is a partial x, partial y? It's an area. The area I'm looking for is the area of this disk. How do I know what that area is as a function of the change in the radius of that disk? Well, that actually doesn't look too bad at all. It would be the circumference of this inner circle. It'd be the circumference of that inner circle. And let me make sure I don't screw this up. That's 2 pi r. The circumference of a circle is 2 pi r. Right? Okay, now again, what is the area of a disk when that disk is infinitely thin? It would be the circumference times the thickness. There you go. That's it. Okay, so to turn this double integral in x and y to an integral of just r, all you do is, wherever you see an x and y, you plug in, you know, use this formula to figure out what r is. We'll worry about that later. But this partial x, partial y, all you do is you write 2 pi r dr. There. Now again, the way you make steps in x and y needs a scaling factor when you go to net change, right? Change in r. It needs a scaling factor. That's the scaling factor. We figured out the scaling factor by figuring out what we're trying to, you know, how does this thing grow? We needed to know that it's an area, and we need to know how the area grows. And that's where we get our 2 pi r. Okay, so anyway, so there you go. Okay, I hope that made sense, because now, cha-ching, dx, dy, dz. Right. Now, actually, this isn't too bad. You see that as we were starting out with some, you see that change in x, change in y, change in z, it's a volume, right? It's a volume element. Now, as you make more and more volume elements, what you see is, instead of a circle, you see a sphere, right? That's in red. Now, how does that volume change as you step along in integral space, as you're adding up those areas? Remember our one-dimensional case, as you add up planks, but you're doing it in 3 dimensions. What you're doing is, you're making the sphere thicker. So how does that scale, instead of x, y, and z, how does it scale with net, with r? Well, it scales as, here, let me just write this down, because again, I think I have it in the picture, but it's not in front of me, so I'm getting a little confused. Just like our example in 2 dimensions, in 3 dimensions, the volume, what you're doing is calculating the volume of that shell, right? The inner sphere is red, and as you take steps as you are evaluating this integral, and as you're adding more and more elements, you're scaling dx, dy, dz as a volume. So what's that volume? That volume is, of course, the surface area of the red sphere, and that would be 4 pi r squared. And then, of course, the surface area times the thickness of the shell, which is dr. Is that right? I better make sure that that's, yeah. Is that right? I better hope I've done this right. I'll know when I start looking at the images. Yeah, I've done that right. Okay. Okay, and that's it. That's the Jacobian. All right, so let's go back here. The fact that instead of x, y, and z, I've got vx, vy, and vz, and instead of change in r, I got change in v, that doesn't matter. They all represent the same thing. Just like r is the square root of x squared plus y squared plus z squared, v, net velocity, is the square root of vx squared plus vy squared vz squared. It's all exactly the same. Okay, since it's all the same, this is 4 pi v squared. There you go. All right, now what does that mean? That means that the probability distribution, this is the real Maxwell-Boltzmann distribution, by the way. And I was kind of stupid. I should have had partial b there. Okay, it's 4 pi v squared. That's the Jacobian. Sometimes on exams I'll write out an equation and it'll ask you where the various parts came from. Okay, that's the Jacobian. That's from the fact that we live in 3 dimensions. Here is the normalizer. And it's to the 3rd power because we live in 3 dimensions. Here is just the business end of the Boltzmann equation. Get rid of that. Not too bad. This is, I know it's kind of a lot. It's probably one of the bigger equations you've ever dealt with, but I mean, it's not really that bad, is it? Okay, and there you go. Ta-da! Now what? Okay, we got a couple of things. Now that we have this, now we have to start thinking about what you can really do with it. Now, I remember I began this lecture by saying, I know this looks kind of abstract. It certainly was. Now we've gotten this into, although it's a little on the complex side, but actually let me point out, this is just a bunch of constants, that's some constants. It's mostly constants, right? Can you plug in pi in your calculator? Can you say Siri multiply pi by 4? Can you do that? I think you can. So for the most part, this isn't that bad. It's just got a bunch of constants. Now this is a mathematical something that you can do a lot with. You can graph it, you can integrate it, and we're going to do all that. First thing we're going to do is graph it. But when it comes to integrating it, let me foreshadow, we're going to do that today as well. If I integrate this thing from 0 to infinity, I better get the number 1, right? Remember that this is a probability distribution. If I integrate this, which is this, from all possible velocities, which would be from 0, because you can't have a negative net velocity, you can have an upper limit of infinite velocity, that's sensible, I better get the number 1. And that means that a molecule is either moving or not moving, which has a probability of 100%. Okay, so we're going to integrate this. Now, before I do that, just to make you relax a bit, let's graph it. And we're just going to graph this portion. I don't know that you can graph it partial, that doesn't make sense. We're going to graph this guy right here. Now, like last time, this is going to be, again, it's going to be a little rough. I'm going to draw some graphs from my notebook, and then I'm going to stand back, and then I'm going to put like something from a paper, you know, something real. But again, I have to have something I can work with, something I can see right in front of me, or I'm going to get really confused. And I'm still like, I'm kind of shaking in my boots about how that last thing I just did with Jacobians. See, I don't know. I don't know if I'm going to have to like redo it or not, because I just don't know how I did. So, and again, I promise you that, you know, my graph hopefully isn't too bad, but I'm going to overlay this with real data. And of course, this is in meters per second. Always use SI. And I'm going to show you on top, I'm going to show you the effect of temperature. And again, you're going to have some nice looking graphs that are going to get off the internet and then splice it into Adobe Premiere. Adobe Premiere is how I do all this. On the bottom is a function of mass. And I'm going to use krypton, argon, neon. And again, my drawing here is approximately correct. You know, one reason that I write things out and I don't PowerPoint is so that we write together. So I'm hoping that you're not using these videos as like, well, I don't need to take notes. I do this so that we write together so that we keep pace with each other. It also helps you remember things to write things down. I know you can listen and watch like a lizard can for that matter, but to memorize, unlike a lizard, you need to write it down. It's going to help you remember things. All right, anyway, okay. So last thing I need to do is write this. So maybe you're doing what I'm doing, or maybe you're going to wait for the graphs to appear. I'm almost done. Almost done. I'm talking like an idiot. KR, AR, and neon. Okay, all right, so there we go. Okay, now I've got the digital graphs up there, which hopefully look very nice and professional. Here's what I want to point out. There's three things to point out. Number one is that, I think I mentioned this Monday. I don't remember when I mentioned this, but the graphs they're almost bell-shaped. They're almost bell-shaped, but they're not quite. They're a little skewed. They're a little bit skewed to the right. They're like a bell curve that's been like grabbed from the top and pulled over, right? And so that's kind of bad. That means that the mathematical analysis of these things is actually kind of tricky. But remember, you want degrees, you want a college degree in a STEM discipline, so you're going to have to deal with it. And a lot of things work this way. Okay, so that's number one. It's skewed. It's almost bell-shaped, but not quite. It's got a skew to the right. And remember when I tell you, this will be in the next lecture, remember when I tell you that means is that the average, let me give you a specific example. The average is not at the very top of the probability distribution. It's not at the apex. It's actually slightly to the right of that. Remember that one. Okay, so there's that. Next thing, you can see how the velocities go higher with increasing temperature. Now, you know that from plugging in a different temperature into the Maxwell-Boltzmann. You have to plug in a mass for like krypton or argon or whatever it is, or oxygen. And that's actually all you have to do. Then you just graph it as a function of velocity. So that makes sense. If the temperature is higher, things move faster, right? So cool, all right, that makes sense. All right, now on the bottom, you can see what mass does. These are all done at the same temperature. You can see that neon, which is light, is moving faster. Argon is heavier and it doesn't move as fast, and krypton is the heaviest of all. So again, it really makes intuitive sense. You still see the way that it's a skewed bell curve, and most importantly, you see those velocities. Those are gigantic numbers. I mean, this always kind of freaked me out. Gases are moving 1,500 meters per second. That is bombastically fast. By the way, the speed of sound, I'm going to speak off the top of my head. I should. Siri, anyway, too late. I believe the speed of sound is around 700 meters per second. And if that's wrong, I'll do some digitals, something, but anyway. Gas molecules do move faster than the speed of sound. They don't spend a lot of their time moving faster than the speed of sound, but they do actually do it. And that's just a really weird thing. I can never get over that, but I'm looking at it right now. So gas molecules can, in fact, move faster than the speed of sound. So that's all I've got to say about that. And we've got a little bit of time left, so now we're going to have to start doing some bloody mathematics on probability distributions. So the first thing I can do is, for one, I want to see that the probability distribution is properly normalized, and I think we have enough time to do average velocity. So we're going to do those two. I'll probably repeat it next Monday, and then we're going to do some more advanced things. I think we're going to get to that pressure calculation where I told you, I've been teasing two things, right? That you can move faster than the speed of sound, and I also was telling you that if you tell me, I have a gas and the mass is 32, that would be oxygen, right? O2, 16 times 2, 32. If you tell me that, I can determine the pressure at room temperature. That is a calculation. I think we're going to do that on Monday. Kind of cool, right? You just tell me the mass and I know the pressure. Anyway, let's see. What do I want to do here? here. I am actually going to, I want you to see that. I want you to see that equation, and I'm going to integrate it on the bottom. So I'm going to make these graphs go away. I'm going to clean the board. I'll stop the video and clean the board. Alrighty. Okay, so I'm back. Let's check that this thing has the property of being normalized. Now, remember that normalization means that when I integrate this probability distribution over all possible values, that I get the number 1. I should be able to do that. Now, what do I want to say about that? Recall that, well here, let me write it down. Let me write that down. I'm being cheap. I'm writing over what I already wrote. Sorry about that. Let me write down what I should get. And, of course, so I'm going to integrate this thing. And what I want to do is verify that I get the number 1. Now, what I can do is I can already tell you that this is not 1. In fact, I believe what I've got here, I believe what I got is 0. What did I do wrong? I'm doing it again. I'm intentionally making mistakes. The lower limit is not 0. Remember that has units, meters per second. The lower limit is not minus infinity, it's 0. Because this is net velocity, there is no such thing as negative net velocity. Remember, I'm going to put that on the test. I'm going to write out an equation that looks fine, but it gives the wrong answer, and you have to tell me why. That's one of my tricks. Look out for that. Okay. Again, I've started here. This is properly normalized because it has a normalizer. When it's integrated, it should, integrated over all values, I should get the number 1 because it's been properly normalized starting from the Boltzmann equation. However, I could have made a mistake along the way, in which case then this will not integrate to 1. Now remember that this is my normalizer right here. But maybe the Jacobian, maybe that does something. Maybe that messes it up, right? So that's what we're going to double check. So we're going to integrate this and see whether we properly get the number 1 or not. Now, okay, there's a couple things you got to know. For the most part, I know this looks fearsome, but it's mostly constants. Let's look at the constants. They're right here, and they're right here. Should have brought a different colored pen. Anyway, okay. Those are a bunch of constants. Let's group those together, and I just like to call them Q. So I'm going to get rid of those. I'm going to rewrite the integral. So I'm going to take all the constants out, because why wouldn't I, right? You don't integrate constants. So let me do that. So we're going to integrate this thing. Again, we've already established the proper limits. And what I'm going to do is I'm going to take out all of those constants so I'm not confused. I almost did it again. That time was an accident. Anyway. Okay, proper limits. Q is on the outside. So what have I got? I got v squared e to the minus mv squared. I can't take out the constants here. That doesn't work. Okay. And of course Q is 4 pi and all that other stuff. Okay. So let me make sure I did it right. All right, yeah. Okay. You're on the test, and this is what you have. And there's about a 50-50 chance that that is exactly true. Or what I'll do is, probability distribution of kitties, which is probably what I'm actually going to do. So anyway, so how do we deal? If this is the test, do not be going on the internet. Right? You look at the identities. I'm giving you the identities, but you have to use them correctly. What is the identity? I go on Google and I find this one. Now again, on your test, you're going to have a whole bunch of identities. You better identify the right one. Now, one of the number 1 things to look out for are the proper limits. That's the number 1 thing to look for. Okay, anyway, before I blabber on more about that, let me just write it out. Okay. Now again, on the exam, you're going to have plenty of these. Take the constants out, and that helps you recognize what's the right identity. Look for the same limits, right? I'm not going to have you, I don't play games with the limits, that's cruel. Then you got to be able to know that v is really x. So I've got a v squared here, I've got an x squared there, that looks good. And this looks like minus ax squared, where a is m over 2 pi kt, and this is minus ax squared, where again a is over 2 pi kt, and then here's the answer. That's the answer. Now let me tell you a common mistake. There are two common mistakes. One is to think that now you apply the limits. No, the limits have already been applied. This is the answer. This function is integrated, and then the upper limit minus the lower limit gives this. You're done. Do not try to apply limits. Besides, what would you apply them to? There's no x in here. This is the answer. Okay, that's number one. The next thing is, of course, is figuring out what a is. We've already talked about that in the previous example. Let's not worry about that. The mistake, the second mistake, the real mistake that people often do is to forget that you took a bunch of constants out. Okay, let me just go ahead and do it, and you'll see a little bit more about what I mean. So 1 over 4 pi. Okay, so 1 over 4. There's nothing to do with that. You have to recognize what a is. Now we've already done an example, so I won't waste your time. A is not minus. We talked about the minus. It's m over 2 pi over 2 kbt. Remember that we ran into this. There was a previous example when we were evaluating the normalization part. That's when we saw our previous use of an identity. Anyway, okay, so that means that I've got an m and 2 pi kb t on top. Okay. And there you go. You got 60%, maybe 70% if I feel good. What? Why not 100%? Because you did what I just said you did, you forgot the constants. Right? This is everything but the constants. Now you got to put in the constants. 4 pi. Okay, now I'll go to the other side. M over 2 pi kbt. And I see, you know what, look what I did. Look what I did, I made a mistake. That's a cubed. Okay. Cubed, 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 cubed. I really screwed that up, didn't I? Good thing I caught it. Okay, so this is the real answer. And this sucks. Oh, no. What am I going to do with this? Okay. Two things. If this is on the test, you know what I want you to do? Stop. This is the answer. This is the answer. By the way, this is correct. Stop there. I know what you want to do. I know you want to simplify it. If you do, and you get the right answer, which is 1, cool. But what if you simplify it wrong? You see, the thing is, the reason that we're obsessed with simplifying things is that up until recently, people didn't have calculators. When most textbooks were written, those were written by old geezers who did not have calculators. Seriously, this stuff is that old. So you're always taught to simplify things. Well, we have calculators now. In fact, I can just say the damn thing into Siri, and it gives me the answer. I bet I'll try that later. Anyway, write this down and stop. Okay. If you simplify it, though, if you simplify it and you see that you got the number 1, then cool. Then you're confident that you got it right. So maybe you do want to do it, but I'm going to leave that up to you. Right? You got to make decisions. All right, but for the purposes of this class, I'm going to verify that it is correct, and I go in steps. Okay, you know what? I've said the 4's canceled. Then I've got pi square root of pi. So what I'm going to do is I'm going to bring that pi squared in, and so now what I've got is I've got 2 pi kb t. See, everything is cubed. Everything is cubed when I bring that pi in. And then what I've got, I'm just going to write this down again. is I'm a victim of different symbologies. This symbology with the square root sign in the interior to the third is the same as to the 3 halves. Same thing on top and bottom, same thing on top and bottom. Everything cancels, it's 1.0. Okay, so there you go. So it's 1, it's normalized, it is correct. The equation is correct. So everything has been properly normalized. The Boltzmann equation was normalized, and my derivation of the Maxwell-Boltzmann never screwed that up. So everything still integrates to 1.0. Now, there's another thing I want to point out. You saw how I had all of these terms cubed in the square root thereof. Is that the same thing as all these terms to the 3 halves? Here's how you do it. Get your calculator. If you're not, so this is like an identity, right? Are those the same thing? Here's what you do. Get your calculator and pick a number like 5 or 7. What you do is cube it and then take the square root. And then compare that to 5 or 7 to the 3 halves, right? Just, punch, punch, punch. Are those the same number? If so, then, the manipulation you saw me do is actually correct, and the end result is 1.0. Obviously, I was correct in what I did because, for 1, it's right, and for 2, I get the right answer. But I want to point out to you, because this is going to save you a lot of trouble. When you have some kind of algebraic manipulation and you don't know whether you're doing it right, plug in numbers. Never use 2, never use 1, because 1 squared is 1 and 2 squared is 2 plus 2. You can run into problems with those. Pick an odd number, like 5 or 7. Again, is 5 cubed and the square root of that, is that the same as 5 to the 1.5? If that's true, then my manipulation was correct. Look out for that. Okay, last bit. I see we're out of time. Let me show you where we're going with this. Showing that this is normalized means that the equation is correct, but that's not useful. I kind of could have assumed that, right? I'm not going to come in here and mess everything up. Let me show you what you really want to do with it. And I'm not going to do it. We're out of time. I promised you that we would not use up all of the time, and I may have already screwed that up. Here is how you calculate average values. Now, I know that in middle school, you learn to calculate the average of a couple of numbers by adding them together and dividing by the number of numbers. That is not what a college student should know, should do. What you should know is that averages of observables, remember y is our observable, energy or velocity, an average value is an integral over all possible values, let's assume from 0 to infinity, of its probability distribution times it. And of course, I'm integrating, so I have a partial. This is the correct mathematical definition of an average. Not taking a bunch of numbers and adding them up together and dividing by the number of numbers. Now that does work, but it depends on the nature of the probability distribution. That works when your probability distribution is flat. It's a flat or bell-shaped. We have neither with Maxwell-Boltzmann. That's why I told you that skew really messes things up. So, to calculate the average velocity of a gas, you see that we're going to do the same integral, but instead of v squared, it's going to be v cubed. We're going to get, now I'll do this next time, I'm out of time. We're going to grab an identity, work it, not forget our constants, and we're going to figure out what the average velocity of a gas is.